Let's continue. So, as a practical case, I have to, yes. So, I switch to solid state now, okay? A solid state problem. Looking at this well-known compound, so calcium with C2, calcium C2 actually, CaC2. So, here you have a representation of the unit cell, the conventional unit cell. So you may see in white the calcium atoms. So in a CFC structure, and with the dimers in black, dimers of carbon. Okay. So it's very easy to rationalize this system. So you may use the Zintal-Klem concept. So as calcium is belongs to the block S, or the S block, he will give his 2 valence electrons to the carbon sublattice. Okay, so you may write Ca2 plus C2 2 minus. So Ca2 plus follows the octet rule. You have the same electronic configuration than the noble gas before, so you should be argon actually, I think, but you have to check. And you get this formally C2 2 minus. So C2 2 minus has 10 valence electrons, so 8 coming from carbon plus the 2 minus charge. So here's the isolate electronic to N2. It's exactly the same. So you may understand why CaC2 is diamagnetic only by counting the electrons. You will feel this energy diagram up to this 3 sigma level, up to here. So here will be the HOMO, highest occupied molecular orbital. And the pi star, here the pi star levels will be the LUMO levels. With a big gap, a huge gap between the HOMO and the LUMO. And you have let's say big distances between the C2 units. So there are, let's say, discrete molecules in a solid state compounds. You may see this compound as this. So here you can understand the electronic properties of this compound easily. So let's switch to another case. So now is with uranium, UC2. And you see that when you substitute calcium by uranium, the carbon-carbon distance increase from 1.19 to 1.38 angstrom. So you may ask why it should increase. So if you take in consideration that uranium may give 4 valence electrons, with so oxidation number of 4. So you will fill by 2 more electrons these levels, okay? Yeah. And you have to remind that when you occupy antibonding level, of course, you will increase the internuclear separation, the internuclear distance within the C2 unit. So only by using this simple diagram, you may explain the geometrical parameters that you may find in these uranium C2 solid state compounds. Okay? On the B case, so I put here homework, so let's say that we are at home. So in O2 plus and O2 minus, the bond length, the separation between 2 oxygen atoms are so 121, 112, and 149 picometers. Okay? So why you have such evolution? So let's start with O2. We did O2 already. So O2, you feel this pi star level. Okay? You have 2 electrons here because we have 12 electrons. 10 here plus 2, 12. O2 plus. So what do you do when you do the cation O2 plus? So we remove 1 electron from the pi star level. So which means that the bond becomes stronger. So you should decrease the separation, the distance between the two oxygen atoms. What we actually observed. Okay. And now O2 minus, so the anion O2 minus, which exists actually. So we add one more electron on the pi star levels. So you will have here 3 electrons for O2 minus. Okay, 13 valence electrons. So you will have 3. So as we put one more electron, sorry, in the antibonding levels, you will increase by actually a much amount. You see the operation. You go from 121 to 149 picometers. So only by counting the electrons and by looking at the occupation of the bonding on antibonding levels in this case. So you can rationalize actually the differences in bond length in these molecular systems. So here I am going to talk on the Jahn-Taylor effect in a system. So C4H4. So C4H4, I am going to talk on cyclic C4H4. And it's if you want to understand the electronic structure and the geometrical parameters in cyclobutadiene, actually, you may study this simple system H4, a square planar D4H H4, which is a model for the pi system. Why you may use H4 as a model? So if you look at C4 H4. So you have you may start from a square actually of C4 like this, and if you look at the pi system, you look only at these orbitals. Okay, the orbital perpendicular to the plane of C4H4. This one, you see, for the carbon. So we will use only one orbital on the 4 valence orbitals of carbon, because we want to study only the pi system, As we have 4 carbon atoms, we should get 4 molecular orbitals, 4 pi molecular orbitals for this system. And looking at only the topology, we can look at only this system, because here each hydrogen has this orbital, and you see by symmetry they are the same if you do not take in account the symmetric plane containing C4H4. They have exactly the same symmetry. Okay, so we can only look at this system, a square planar H4, which is a model for this pi system. So how to do that? So you start from the square of H4. So I rotate here just to show more correctly the 2 fragments, so in red and in blue. So you will have 2 H2 fragments. So we did already H2, but we did H2 at the equilibrium, right? So we will get a bonding orbital, sigma j, and an antibonding orbital, sigma u star, remember. But here you have a long distance between 2 hydrogen atoms. So what we can draw in order to generate the energy of these orbitals for the F1 and F2 fragments, we can draw what we call a Walsh diagram. So what is a Walsh diagram? So you start from H2 at the equilibrium distance. So here is the energy, or we can use EV. Here, let's say that we have 0.74 so angstrom. So here the distance in angstrom between two hydrogen atoms. Are you following me? It's okay?
Yeah.
So I have H2, so two s orbitals, so two molecular orbitals, the sigma and sigma star one. So I draw the sigma here and the sigma star one, like this. I can draw the orbital, so one is like this, so the in-phase combination, and here the out-of-phase combination. So where is minus 13.6 eV? Here, in this diagram. Huh? Below where? Below the sigma? Where do you put minus 13.6 eV on this scale?
The one in what? The sigma 1?
No.
Between
Who say? Between? Yes. Yeah, it's between. Yeah, of course. But it's not exactly at the half. It's just below. It's around here. Remember, this value is the energy of a 1s hydrogen orbital. Okay? And we are doing, we stabilize one molecular orbital and we destabilize the other one. But the destabilization is bigger than the stabilization. So you should know where is, around roughly, where is minus 13.6 eV on this diagram, approximatively. So I continue like this, okay? So now I increase the distance between two hydrogen atoms in order to get the molecular shape and energy of this F1 and F2 fragment. There is no interaction here. Let's say low, a small, very small interaction. So what's happened? If I increase the distance here, the overlap, the positive overlap, goes to 0, almost 0. So the energy of this level is going to minus 13.6. So, for example, here, let's say that we have 1.5, I don't know, 2 and after 3, if it doesn't matter. So we do a correlation between these levels, like this, and for infinity, you will have exactly minus 13.6 eV. Okay? On this one, you have antibonding out-of-phase combination. So when you increase the distance, the overlap turns to 0. So this orbital is stabilizing and is going here, like this. And here, so you have a degenerate. So what I prefer to do is to put one level here and the other here. They are almost degenerate, let's say. But the almost in chemistry, it's around 3 angstrom. You are at the infinite, on an infinite system. Okay? So we know already the shape of these orbitals. So this one is like this. On this one, you can draw this like this. So they are in phase. These orbitals are in phase, but they are non-bonding because you have a big distance, a huge distance between the two hydrogen atoms. This one is out of phase, and this is a non-bonding orbital too. Okay? So we have our orbitals. So now we can draw the molecular orbital diagram for H4, square planar H4, like this. So it's sigma, and let's say I put sigma star. Okay, sigma and sigma star. So this one is F1. F1. Looking at this slide. So the other will be also sigma and sigma star. At the same level, you have only to switch your fragment by 90 degrees, and you will get the same. So now, if I draw correctly F1, Okay? So we have F2 now. So in the middle, we have our square of H4 in the middle. You add F1 with F2. So which orbital can interact with the other? So for that, you have to take into account the symmetry of your square. But let's say the symmetry is that you have in common for the two fragments. So you see that for the square, you have an inversion center. For this fragment, you have also an inversion center. Okay? On this one too. So let's take the inversion center first. So for this orbital is symmetric. Looking at the inversion center, okay? So I put S, symmetric. This one is antisymmetric, okay? This one is, so this one is symmetric, and this one is antisymmetric. So we know already that this orbital will not mix with this one, for sure. So it's done. We can use now this plane, for example, okay? So we can call this plane, for example, P1. Is fragment 1? Yeah, okay, P1. So for P1, this one will be symmetric. This orbital. Yeah. Looking at P1. You understand what I am doing? Yeah, yeah, P1. So symmetric. Yeah. This one, symmetric. This one. Oh, no. With P1, okay? Let's symmetric. And this one, antisymmetric. So I am doing inversion center on P1, okay? And after you can use, why not P2? This one. So symmetric, symmetric, antisymmetric, and symmetric. So it's done. You can continue at home if you want. So you can see that this orbital is ASA, alone. So we know what it's doing. This orbital is orthogonal to this one, and this one. So it will stay exactly at this level. You agree? Yeah. So I draw now my square, and I put the coefficient here, here, and here. Actually, you know the value of this coefficient is 1 over square 2. And here is, so here is 1 over square 2, and here is minus 1 over square 2, okay? So this one, same, is AAS. So is alone, so you have to draw like this, degenerate, like this. Okay. So we find already two molecular orbitals, which are degenerate. They are degenerate. Two wave functions with the same energy. Okay. So now this one, SSS, can interact with this one. We know that it's a two orbital and two centers, as in H2. So you will have a in-phase combination. So I can draw like this. So what is the value of this coefficient? The coefficient.
1/2.
Yeah. Yes. Yeah. Yes, of course. Yeah. Or 1 over square 4, so 1/2. Okay. And you will have an outer phase combination here that you can draw like this. So it will be this here minus this one. Okay? So you have to black this. We're done. It's done. So we did H4 square. Okay? So we have a bonding level, two non-bonding level, and one anti-bonding level. So what about the electrons now? How many electrons? we have in H4 4 electrons. Remind that we want to study C4H4, the pi system. How many pi electrons in C4H4? 4. Okay. So 4 electrons. 1, 2, 3, and 4. You see that in this case, we should have what we call a radical, a biradical system with 2 unpaired electrons. And this situation is very unstable. You may not have such system. It's unstable. We know that it's unstable actually. It will dissociate in 2H2 or maybe in H3 and H minus. You have to do calculations. Anyway, you will have a fragmentation. And this situation is called a Jahn-Taylor. Will lead to a Jahn-Taylor distortion. Because you don't feel this degenerate level. So the molecule, the system will find a way to distort in order to open the gap to get 2 non-degenerated levels. So I will show you a way to do that. So we start from a highly symmetrical system, and we are going now to distort this system because the system is unstable. You understand? Because you have this situation. Only 2 electrons and 2 degenerated levels. You may have different type of distortion starting from a square. The first one, so now I took a square like this. You start from a square and you go to a rectangle. Okay? Like this. Why not? You decrease the distance between these 2 atoms and you increase in the other way. In chemistry, we know that we are doing double bonds and single bonds. This is what we are doing. So let's draw again. So I took only these 4 levels. Okay? So 1, 2, 3, 4. So it's pi 1, pi 2, pi 3, and pi 4. I switch to C4H4 now. I have already the shape of the molecular orbital, so it's okay. Okay? So here is for the square. It's for the square. This is in D4H space group. You have a C4 axis perpendicular to the plane. So what's happened when you decrease the distance here? So look at the orbital here. So you increase the overlap, the positive overlap here. Okay? But you increase, yeah. But when you elongate it, you will decrease the positive overlap. So you should have the same energy here. So I can draw. You understand here? It's okay? You increase, you decrease, the overlap change. Using Hooker calculations, you will find exactly the same energy level. So now, this level, so let's take these 2 orbitals. You know that when you have 2 degenerated orbitals, you may have 2 other orbitals, which are solution of the Schrödinger equation. If phi 1 and phi 2 are solutions of the Schrödinger equation, you may construct phi 3 and phi 4. Phi 3 will be phi 1 plus phi 2, and phi 4 will be phi 1 minus phi 2, something like this. You may generate other. So what you can do, you add this one with this one plus this one. You follow? This one plus this one. So now I draw my square. This one plus this one, I will find this orbital. They are the same, exactly the same. When I mean the same, they have the same energy, these orbitals. Okay? So you have this for pi 2, and for pi 3, it will be this one. This combination. In phase, out of phase. Okay? It's just a trick. Because for me, it's very simple to see how the energy of this level will move, will go, when I will start from a square to a rectangle. So, starting from the square to the rectangle, so I decrease here, okay? I decrease the distance. So, you will stabilize the orbital because the positive overlap will increase. Agree? And here you have an out of phase combination. But you increase the distance. So if you increase the distance between these two carbon atoms, you will decrease the negative overlap. Right? So you will also stabilize the orbital when you start from a square to a rectangle. So pi 2 is going to be stabilized here, pi 2. So I can draw it like this. Like this. And now look at pi 3. So I start from the square to the rectangle. So you see that here is antibonding. You decrease, so you destabilize the orbital. And here is bonding. You have the same sign. It's minus minus for this case, or plus plus here. So as we increase the distance between two carbon atoms, we will also destabilize the orbital. So we are opening a gap between pi 2 and pi 3. We open a gap. They are no more degenerated because you lose your C4 axis and you keep only the C2. So let's do it like this. Up, up. Okay. So you will get these orbitals. And for the last one, so which is like this. Okay, if you look at this one, you see that when you decrease and increase, it remains at the same energy. Okay? So pi 4. I don't draw again. So, number of electrons. We still have 4 electrons, of course. We are starting from ideal C4H4. 1, 2, 3, 4. And here we have 1, 2. In the ground state, 3 and 4. So the HOMO is here, and the LUMO is here. Do we gain energy when we go from a square to a rectangle? Of course. You see that we gain this, actually. If we call the stabilization delta E, the electronic energy in the first approximation is 2 times delta E in stabilization. So it's a way to understand why C4H4 is not a square but a rectangle. But we know that with Lewis. We don't need to use this because when you draw Lewis structure of cyclobutadiene, you have a double bond and a single bond. But you can draw another resonant structure like this. So we are not sure that we have a rectangle. It could be between this. And between is a square, but the square is not stable. It's unstable. For the ground state, I mean. For the ground state. So you can explain why you have a rectangle. You have a short and a long distance using these molecular orbital diagrams following the Jahn-Taylor effect. One more. So here I did, so it's done for C4H4. And now we can look at this cation, S4 2+. This cation has been prepared in solid state, so with an ion, of course. So S4 2 plus, how many electrons for S4 2 plus? I will finish now. So S4 2 plus, how many valence electron? 26. 26, 20, oh, 26. Oh.
No, 22. 22.
22! Okay. No, it's not 2 minus, it's a cation. It's 22 electrons, okay? So 22 electrons, so let's draw S4. So you can draw like this, why not? So I start from the skeleton. So 22, I have to draw 11 pairs, okay? 11. So 4, so you remain 7. 1, 2, like this, no? No, it's not good. So 3. So what I do now? How I do?
Well, you can draw all the lone pairs except one.
Except one, okay. So I can put one here, and one here, and that's it. And after, you draw different resonant structures, okay? Moving this lone pair, for example, to this side, on the you do a circle. So how many pi electrons now? How many pi electrons? When you look carefully here, you have to figure out that here you have a decoordinated atom, as in H2O, right? With 2 lone pairs and 2 bonding pairs. Okay? One of the lone pair is a sigma pair, and the other is a pi pair, a pi bonding, non-bonding pair, perpendicular to the plane. So you have 2 plus 2 plus 2 pi electrons.
Aren't they hybridized like an H2O?
Sorry?
Aren't they hybridized like an H2O?
No. They are perpendicular to the plane, to the square. Yeah. In this case, and you have 6 pi electrons. You follow? Yeah. 2 here, and 2 here. The other are sigma electrons. So 6 pi. So 6 pi. 2 here and 4 here. So do you think that we are going to a rectangle? Or do we stay in a square structure? We stay in a square structure. And so you may explain why S4 2 plus is square planar. And actually is what we saw, what we determined using X-ray diffraction. Only by counting the electron and looking at these molecular orbital diagrams. You have a case here for S4 2 plus. You have 6 pi electrons, perfect square planar. For C4 H4, you have only 4 pi electrons, so you are in a situation that you should distort your molecule to open a gap between the HOMO and the LUMO, and you will stabilize the energy of your system. You know this effect in solid state is a Peyer's effect. We will see that after next in 3 days. That's it!